Syzygy, episode 106, Star Eats Planet. Welcome back to another edition of the Syzygy podcast. This is episode 106. My name is Chris Stewart, and sitting opposite me at the round table in her office, Dr. Emily Brunsden. Emily, how you doing?
I'm doing well, thank you.
I'm looking at your whiteboard, still blank.
I'm going to give you some ideas to fill it up today.
Good, because it's disturbing. It's just wrong. Shouldn't have a whiteboard, a blank whiteboard. It should be filled with ideas. We have a bunch of stuff that we need to talk about today. In today's episode, we have a very clear topic that we need to get to. It's a little bit existentially terrifying, to be honest, but we'll get there. But before we do, little bit of follow-up. Two things, actually. First of all, we're recording this at the very end of what is apparently, officially, I don't know who decides these things, Black Hole Week.
Black Hole Week.
Do we know who decided it was Black Hole Week? Is that a UNESCO thing?
I suspect it's someone who's involved in the research of black holes.
Probably. I mean, I decided that this is Black Hole Week. So there's been loads of stuff all over the podcast world and the social media world, from science and astronomy and astrophysics-based things, all about black holes. Well, tell you what, we were there already in advance. If you want to know from Syzygy's point of view about black holes, episode 104, just 2 episodes back, we did the whole thing.
We did all
the
black
different
holes.
kinds.
Yeah.
We did all of them. So we were like 2 weeks ahead of that game. So we're not doing black holes today, are we? No. The other thing that we need to go back to is last week's episode, 105, where we talked about everything that's going to the moon, like within the next couple of months. You know, there's lots of stuff going to the moon over the next several years. We just restricted ourselves to what's coming up in the immediate future. And Emily took us through, half a dozen different moon missions that are coming up just in the next, season, spring, summer. But there was one that we missed, apparently, Emily.
Yeah. So I forgot to mention the one that was currently heading towards the moon as we were recording.
Right, and which one was that?
So this is one from a private company from Japan called iSpace.
Right.
So one of the first fully private moon missions to head off. The mission itself was called Hakuto R. Mission 1.
Okay, another very imaginative title. I don't know what about the first part, but the second part, Mission 1. All right, that's ambition. That says there's going to be more than one.
Yeah.
So how'd it go?
Well, set to touch down on 25th of April. It was all going well till about 90 minutes before contact. And then we lost all communication.
Oh dear, that's never a good sign. Do we know what happened?
Not exactly, but it sounds like a bit of a splat scenario.
Right, so the contact was a bit too contact.
Yeah. It sounds like the spacecraft didn't have much fuel left, and we're going a bit too quickly.
Too fast. Yeah.
Meeting the surface at a little bit of a too high velocity.
It's that very last bit that's really hard. You know, getting to the moon is hard enough, but then stopping at the right speed and distance is even harder. Well, look, our sympathies go out to the team. Sorry it went that way, but look, as mission 1, that's a good effort.
Yeah.
You got there.
And it looks like we're going to have mission 2 next year. So,
fantastic. So good luck with that one. But we missed that one out in last week's episode. So glad we covered those bases, because that was happening pretty much as we were recording.
And you wouldn't have wanted to be too emotionally invested in that one anyway.
Well, exactly. Yes, that could have been really sad. Maybe the podcast would have been, and there's really exciting things happening. Oh well. So on to today's topic. We're going to be talking about, as I said, something a little bit sort of existentially terrifying. Apparently, we collectively, the astronomical community, have spotted a planet being eaten by a star. Emily, what's going on? Who's found what?
Yeah, there's going to be a lot of anthropomorphizing. Yeah. Stars eating planets.
Yes.
So
nom nom.
Consuming.
Yes.
Nom.
Yep.
Yes. So we have observed for the very, very first time, the signal of a planet which has entered the atmosphere, or at least deep enough into the atmosphere of its host star, that it has been completely destroyed and therefore goners.
Okay. So many questions, which I'm sure we will get to. But can we just clarify, are we talking about a planet which is sort of, spiraling down and hitting its star, or is this the star blowing up and going, I'm going to come out into the orbit of you and I'm going to eat you up? Which one of these is it?
It's actually a little bit of both.
Oh, exciting. Okay.
Yeah.
All right. So why don't we start with who? Who's done this?
Yeah, so this is from Kishley, D, and Al. So they all, well, not all of the authors, but several of the authors, and the lead author certainly come from MIT.
Okay.
So they have been working with the couple of the telescopes and the Palomar Observatory, which is in Southern California, and the big one that kind of set in motion, let's say, this whole kind of chain of events of observing, which we're going to look at, was the Zwicky Transient Facility, which is one of the famous in the astronomy world sort of transient surveys. Now, you're going to ask me the next question. Unless you already know everything about transient surveys, and we can just move on.
What is a transient survey? I mean, can I take a guess?
You can.
This is a survey of transient being something which happens only over a short-term period, like something going in front of something else, for example.
Indeed, yeah. So basically what we're looking at, and there's loads of these surveys that go on all around the world, looking at the sky and saying, does anything unsurprising happen? Does anything go suddenly bright?
Right.
Does anything go suddenly faint?
Right. As opposed to, hey, look at all these things. It's, but what changed from that frame to that frame really quickly? Yeah.
Yeah. So Zwicky's one of the famous surveys that's...
Who was Zwicky? Zwicky?
That's a good question.
He was a name.
Yeah.
He was, if I remember correctly, he was actually not a very nice guy. I'll have to look him up. I'll look him up and I'll put the note in the show notes. He was an astronomer and a very famous astronomer, and apparently, bit of a character. Anyway,
so transient surveys are often set up to look for things that you might expect to be kind of sudden astronomical events. So supernova's a big one, right? Flares, stars that do massive flares. We've got even binary star mergers. You might see flashes from them. So all these kind of things that you can't predict. You don't necessarily expect that this particular object is going to go flash right now. So what you do is you just wait, you survey and you wait to see one. And then when you see one, you can trigger alert systems for follow-up work and so on.
Right. So transient can mean, like it means temporary, but temporary can mean different things. Temporary can be really quite quick, or I'm guessing, a supernova happens quite quickly, but the effects of it go on and on and on. And so transient could also mean changing over a longer period of time too.
And actually, while I gave you just 3 examples of very high energy events, there's also loads of them, like near Earth objects can be classed as transients because they sort of come into view quite suddenly.
They come and go.
Comets, things like that can be picked up. So there's lots of interesting stuff that changes night by night in the sky.
Speaking of interesting stuff that changes, can you hear that? Thunder. Yeah. There's rumbles of thunder going through.
Although the RAF were doing some of their practice. So I've always got to think twice.
There is a storm out there. Yeah. Anyway, if it all suddenly goes very crackly, listener, you know what happened. We got hit. Okay.
So this survey is it's one of these lovely surveys. It looks at the entire northern sky over the course of about 3 nights.
Right.
So a huge field of view on the cameras, and they just kind of point at that bit of sky, then take a picture, and then next bit of sky, and then next bit of sky.
And once upon a time, these would have been things which literal human beings with literal eyes would have looked at from one plate to the next and gone, that bit there, that bit got brighter. But presumably, we don't do that anymore. Yeah. Presumably, we have machines that do the looking for us.
Yeah. So we've been made redundant from the observing process itself. So the whole telescope's, robotic. It just does its thing. You just go, I haven't looked at that bit for a while. I'll go and look at that bit. So the actual survey mechanism is robotic. And then, yes, the detection of something being different is all done by computers. So all done looking at how does this change this frame from the last time I took that picture? Is there anything interesting? If there is, I'm just going to fling a little email to whoever to say, hey, look, I found this thing. Is it interesting? Go and have a look.
Cool. Just be a little bit careful not to go too far
away.
Too far that way. Just
yeah.
You can move around a bit, but you were tending to lean a bit too far over. So, okay, from this survey and from that instrument, we have seen a transient event. Yeah. Fantastic. But somehow we take the leap from that, we've seen something, to, you know what that was? That was a star gobbling up a planet. So take us on that next bit of the journey then. How do we know this?
Yeah, so this research team were particularly looking at things like binary star mergers. So 2 stars that are in very, very close orbits that, again, you've got some kind of energy loss mechanism. So they're spiraling down and eventually merge.
And what kind of, like, that kind of energy loss mechanism? Like, why are they spiraling down?
Well, it's a sort of, you get to there's two different effects that happen when you've got an orbit, effectively. And this is going to be true when we talk about the planet, and it's going to be true when we talk about the Earth and the Sun. Yeah, so to move an object further away in its orbit, then you need to, the easiest way to do that is to change the mass of the central object.
Okay.
Right? So in the case of, say, a planet going around a star, if the star gets less massive, then that planet will move further away.
Right, with its just present energy and speed and so on.
You're losing angular momentum out of the system, effectively.
Right. Okay.
That's what happens.
Okay, so that'll fling you out a bit.
Yeah, so that'll push you out a bit. I guess equally, if you added mass to that centre of that system, then you would move closer.
Okay, sure.
That's a harder scenario to imagine in terms of stars and planets. But
sure, I'm struggling to imagine how you would just suddenly throw or remove a bunch of mass from a star, but I'm sure there are mechanisms.
But you've also got a competing effect with that, which is drag, so friction.
Okay.
So I think, as we've mentioned, probably quite a long time ago, so it's worth reiterating, the sun doesn't just stop. It's not a solid sphere and that's like, this is the sun, here is its edge, and then after that is just completely empty space.
Right. It looks, and in all the pictures, it just looks like a ball, but it's got a very hazy, fuzzy edge to it. It goes out a really long way.
Exactly. I mean, solar physicists would argue that the Earth, indeed orbits inside the atmosphere of the sun.
Right. Okay. Yeah.
To some extent.
It's a very long way away from that image of the solid ball. Yep.
Yeah. So of course, if you can imagine you are orbiting inside the atmosphere of something, then you get drag. So that's friction that slows you down. You're losing energy. So if you're losing energy out of your system, then indeed you're going to start moving in as well as you go. So you will move closer to your star.
The extreme version of that is if you just had something which wasn't orbiting around the sun at all, was just standing still in space, whatever that means, then it would just start accelerating straight towards the sun, right? And so the slower you're going in a particular orbit, slow down a bit, you're going to start moving in towards the sun, which, that's what drag's going to do. And so that's presumably happening to all planets to some degree.
Yeah, and indeed in a binary star system, if they're kind of sharing a little bit of matter as atmosphere, then you're going to get drag effects.
Right.
And if typically these are stars towards the end of their lives, so there might be some mass loss effects as well that are kind of competing. There's all sorts of weird and wonderful systems out there.
Weird and wonderful and messy, and all of these things take you away from the Platonic ideal of two balls orbiting each other forever. That's not the real universe at all. Okay.
So binary stars and binary star mergers happen. So that's indeed what this team were looking for, and that's fine. Then they saw this event, and this event is now the name of this star-planet system because that's how it was detected. Right.
We hadn't paid attention to this place before.
No.
We just went, oh, interesting.
Yep. It's called ZTF. Stands for Zwicky Transient Facility.
Sure. Yep. Makes sense.
SLRN, not sure what those ones stand for. Didn't check those ones. I'm sure they're very interesting. 2020.
Okay.
Because this was discovered in 2020.
Yep. All right. Good. So we have a name. Once again, not a particularly interesting name, but there's a lot of things.
SLRN 2020.
Yeah. There's a lot of things in the universe. You need a pattern. So we've got a name.
We had an event, and it was kind of like a bit of a flash where the actual event happened in May 2020. You had this kind of rise in brightness, and then sort of the object went about a couple of hundred times brighter than it was in previous images. Stayed there for about sort of 10 days or so, and then just really slowly faded, not actually a huge amount, but about 10 times from what it used to be over the next kind of 6 months or so.
Sorry, it went up by a factor of 10?
Went up by a factor of 100.
Oh, 100?
Yep. Or a few hundred even.
Right. And then
sort of sat there for 10 days.
And then slowly came down.
Then slowly came down over the next 6 months, but only about 10, a factor of 10 down. So if it did
it stayed considerably brighter than it was in the first place.
Yeah, so still considerably brighter than what it used to be.
Is that that sounds like a lot, going up by a factor of hundreds. That's a lot of brightness. That's a lot of stuff going on there.
Yeah, I mean, it is and it isn't. And it depends what you're comparing it to. I mean, supernovae are pretty extreme examples.
I'm just thinking about a star. And a star, just by itself, just being a star, there's a lot going on. There's a lot of brightness there. Turn that up by a factor of, let's just call it 100. Just, Sure, it's not a supernova. We've already established in past episodes you don't want to be anywhere near a supernova. Let's just put that in a category by itself, right? But even just turning the sun up by a factor of 100 feels to me like we'd notice that.
Yeah.
That's quite a
that
big
wouldn't be
deal.
good. No, you're right.
Okay.
It would be a big deal
Good.
for us.
I'm glad I'm not imagining that, because that does sound like, oh, something really did just happen there.
Yeah, indeed. So, yeah, it's worth looking into, right?
Sure. Yeah,
Something like that. So this is where kind of the story of the follow-up observations kind of takes place. And I guess this is where I tried to sort of pull out from the Nature paper and from some of the news articles, like this, what are the story of the astronomers doing this? Because you see this thing and you think, oh, that's kind of interesting. That's not how these binary star mergers happen. They're typically a little bit brighter, and they certainly don't tend to stay as bright for as long as this event has. So it's worth investigating, right? It piques your interest.
Yeah. We want to know what's happening here.
Yeah, so the first set of follow-up observations we got came from 2 observatories, actually, that did simultaneous or close to simultaneous observations. We had Keck in Hawaii, which I think we've mentioned before.
Yeah, up on top of the big mountain there.
Yeah, big telescope there. They took some spectra. So we took the light from this patch of sky and sort of broke it up into its constituent wavelengths to see what's going on. What are the chemical elements going on, particularly in this object? Because that gives us a clue.
What sort of things can that tell you? How do the chemical elements come into it?
Well, for example, in the case of a binary star merger, what you'd expect to see is that, okay, there's lots of temperature, there's lots of energy, there's lots of heat. So you expect the hydrogen and helium to be what we call emission lines, which means that the hydrogen and helium got really, really energetic, and then as they've sort of cooled it down and released some photons, then we see loads of hydrogen photons, loads of helium photons from these 2 stars.
Right. There's a particular signature that, I mean, for all the elements, but for hydrogen and helium, we're looking at those particularly because stars have lots of those. And so if 2 stars bang together, you'd expect to see a big fingerprint of, there's a lot of hydrogen and helium getting very excited. That's probably 2 stars.
Yes.
Okay.
So I didn't see that.
Right.
So no emission, no hydrogen or helium in emission.
Right. So that was conversely, weird. Not 2 stars. That's what is.
Yeah. In fact, no emission, which means, excitation of any sort of chemical species at all, really.
Right.
So nothing of significance.
That's odd.
Yeah.
So lots of energy. I mean, it's got a lot brighter, but it's not giving a signature of 2 big things bashing together.
2 stars. Or indeed some of the other things which you would think, you've checked off, okay, it's not a binary star merger. What else could it be? You're next on your list of kind of things to think about what it might be is something called a nova. I think we've talked about nova quite a while ago.
I seem to remember it. So not supernova,
no,
but just plain old nova,
garden variety nova, or even dwarf novae.
Ooh,
yeah. So a nova is when you have a little white dwarf star. So these are the compact remnants of sort of ordinary stars like the sun. You get rid of all their outer layers. They go through this whole process of evolution, and they're kind of this little lump of carbon, oxygen, that sort of thing.
They're not big enough to form really interesting things like, neutron stars or black holes or that kind of thing. They just end up as lumps of stuff.
Yeah.
Yeah.
So you've got one of them kicking around, but you've got one of them kicking around in a binary system again with a bigger star which is currently bigger. So it's a big puffy red gianty star, and that big puffy red gianty star is kind of shedding some of its mass onto the white dwarf.
Right.
And it can cause kind of some instabilities and flare-ups effectively on the white dwarf that we call novae, because they just sort of go, woo.
They're very energetic, but they're nothing like a supernova.
No,
right.
no. Supernova. So supernova, actually, there are types of supernova, particularly type 1As, which are that exact kind of system, except that's what happens when you pile on too much stuff onto the white dwarf, and the white dwarf just collapses under its own mass, basically.
Right, it just starts this whole process of, okay, fine, end of life again.
Yeah.
Whereas the nova is just, this is complicated. This is just energetic. This is uncomfortable.
It's all kind of surface explosions compared to the explosion of the whole star, effectively.
Okay, so could be could be that what they saw was a nova.
Yeah.
Yeah, turns out.
Yeah. So, no, you would expect to see some atomic emission still. You'd
Okay.
expect to see maybe a little bit of hydrogen or helium if that's the atmosphere of the mass that's coming on, or even the carbon that's on the white dwarf. Just something.
Nothing.
Something.
It's not that.
Yeah.
Okay, cross
No.
that one off.
Yeah, and the same for the dwarf nova, which are kind of just smaller versions of the same process. We don't actually know exactly what causes a dwarf nova, but it's small scale.
Similar sort of stuff. It's material in a binary system, material falling onto the white dwarf and causing energetic stuff.
Yeah.
And it's not that. You're not getting any of the right signals here.
So you're not getting any kind of explosive outburst here.
Okay.
So that's kind of confusing, right? So you think, that's a bit odd. Now, I mentioned they were doing 2 sets of observations at the same time. Now, these were both taken about 6 months after the original rise in brightness. The second set of observations came again from Palomar, but from a different telescope. So they were using the 200-inch, which I think is called the Hale telescope. And they were looking at infrared part. So instead of looking at optical, so what we see, going into the infrared to just beyond in the infrared what you see. And this is where they started to see some interesting stuff.
Okay.
So I've got a quote here from the lead author. It says, "We noticed that it was insanely bright in the infrared."
What does that mean?
Insanely bright. So
I mean,
very clearly very scientific.
Yeah. I mean, this is an astronomer who's barely keeping a lid on.
Yeah.
Here. You won't believe what we just saw.
Well, there are other quotes from the lead author saying things like, "I nearly fell off my chair," which love it. It's this is exactly how research works.
This is cool. So why the excitement? I mean, I'm sure when you're an astronomer, anytime you see anything which is like, there's a lot of that going on here. Like, that's interesting, but in a circumstance where we've just seen something and we're striking things off the list, it's not that. It's not a nova. It's not 2 stars colliding. And then you look in the infrared and you see a lot, insanely bright. What does that mean? What information are you getting from that?
So that's telling you that there's, in this case, a lot of dust.
Oh, okay.
So dust, astronomical dust, sort of part, but it's very small particulate matter, usually things like silicates, granites, that kind of thing.
Okay.
So pulverized rocks into very, really tiny particles, like micron size. So I think the typical size comparison is cigarette smoke. Right. So really tiny. This is dust, and dust tends to absorb radiation and re-emit it very strongly in the infrared. Okay. So that's what we're seeing, this really bright signal. And if you kind of add up all that signal and say, well, there's this much brightness in the infrared, how much dust is there? It turns out there's quite a lot.
A lot. Very dusty up
Something
there. Very
like
smoky.
a third of the mass of the Earth worth of dust.
It's quite a lot.
Yeah, so you took the third of the Earth and pulverized it into this dust.
Right. So what does that mean? What are we seeing here?
So we've got some kind of dustiness happening on the outside of the star. Some of it probably came from the star itself.
Are stars generally dusty places?
Well, not typically. I mean, they are in some situations, but you wouldn't necessarily expect it from just the fact that you had this brightening event. So that's another sort of little puzzle.
Eyebrow raised. We have several eyebrows raised now.
So it's almost like you've got several jigsaw puzzle pieces, but there's big gaps in between them, and you're just trying to put in the bits.
The middle part of the jigsaw is still missing. Yeah.
And then so there's some further IR observations that came from NASA's space telescope called NEOWISE. Okay. So NEOWISE is I've already said it. It's a space telescope. It's up there.
It's up there. It's in space.
It's
doing
not
its
James
thing.
Webb. But it's
but it's one. Is it a new one? It's an old one?
No, it's been
Don't
around
remember
for a
us
while,
talking about NEOWISE, but we might have.
I might have mentioned it, but yeah.
What kind of telescope? What's it? It's looking in the IR.
IR,
infrared.
Yep. And observations from that you can sum up in the infrared to see kind of, well, how faint or how big an object would potentially be if it was an impact scenario. Could you have 2 stars that would impact? Would it be a star and a smaller star, a star and whatever?
Right.
You can sort of figure out how much mass worth of energy has been generated out of this event.
Right.
And that number came out to be something like 1,000 times smaller than the sun.
Okay, so we're now well and truly into planet territory? there.
Yeah,
I mean, what's the ratio of mass of sort of your Jupiters to your sun?
Jupiter's about 1,000 times.
About 1,000. I thought it was
smaller than the sun. Yeah.
I mean, Earth's a lot smaller, but that's like we're talking planet size, right?
Yeah. So you put that into the mix. So we've probably got something, or at least the amount of energy that's been released is something about 1,000 times smaller than the sun. Then we do have some images as also. I mean, that was you knew you were going to go and try and take some pictures. What is this thing? What is this thing? Again, from Gemini, which is Gemini South, and which is in Chile. And the images sort of found a tiny, faint, fuzzy blob.
Okay.
In the right place.
Sure.
So
there's something there, which is always nice.
It's always good
to know that what we've just seen actually exists.
Yeah. So you take the fact you've got a fuzzy blob star. We've got a spectrum, and I didn't mention it before, but from those spectra, we can see some really good signatures of what type of star that is. Okay. So we didn't have all that emission that we'd expect from an energetic event, but there's lots of absorption from molecules, and that gives you a really good clue that this is a very cool star.
Okay. Cool in the temperature sense, not in the, hey, hanging out kind of sense.
Yeah. Because so hot stars, you got, like, nothing can exist apart from hydrogen helium on the surface.
As soon as you try to bang a couple of atoms together to make a molecule, they rip apart again. But cooler stars, you can actually get molecules.
You have lots of molecules on the surface, So there's quite distinct signatures of, they even called a molecular band. They just wipe out half your spectrum. And
because the fingerprints of molecules are like complex. There's a lot going on with molecules. There's loads of different ways that they can emit energy, which makes things complex. But am I right in guessing that if you've got this, you've got a picture of a white blob, we can tell it's a cool star, and we just wouldn't expect any of this stuff going on with a cool star like this.
Well, there's no reason for it to do anything super weird, right, on its own.
Sure.
In fact, so we're saying cool. I mean, this is, I've looked up, they're thinking the temperature is kind of around 3,600 Kelvin degrees, whatever.
It's close enough. Yeah, close enough to Celsius,
Compare that to the sun, 5,800.
Right, okay. So it's a lot cooler.
Yeah. And in fact, it's the spectral class of it is an M43.
That means nothing to me. Translate.
Yeah. Okay, so M, very cool star.
Okay.
That's basically the end of the whole spectrum of hot to cold.
Okay.
And 3, the M4 just tells you whether it's like an M5 is slightly cooler than a M4, for example.
All right, fine.
It's just a part of that classification. The 3 tells you it's a giant, so it's really, really big.
Okay.
In the paper, they actually talk about it being very similar to quite a famous giant star called HV 2255.
Oh, that one. No, never heard of it.
Yeah, actually, I couldn't find a lot of information about it either. They said it was famous, but I'm not. Yeah, cool. But okay, so HV 2255 is one of the largest stars we've ever measured.
Like it's on that scale. No, we're not just talking big. We're talking like those videos that you see on YouTube of going from small star to big star, and your brain explodes. This is at the far end of that video. These are big stars.
So HV 2255 they reckon is more than 1,000 times the size of the sun.
Wow, that's pretty big.
But it's not big like you might think. Oh, massive, really hot, raw star. It's actually very, very cool.
It's just
on the
spread
surface.
out.
Yeah, exactly.
Yeah.
So these are stars that are going through the final throes of their lives, where they're still fusing sort of helium and maybe some other things, and deep down in the cores. But they're trying to hold up all these outer layers, but the outer layers are expanding because of the increased photons that are coming from these extra nuclear reactions in the core. It's all of the kind of final death throes in a sense.
And what's the ultimate fate of such a star? What happens when it runs out of fuel?
So, well, it's going through this whole process. It's losing its atmosphere. So it's kind of, the atmosphere is getting so big and so cool that it can't even hold on to its atmosphere. If it gets little shocks of instabilities, and you get mass loss. So it's kind of puffing out, almost like, I don't know, I imagine these kind of like those mushroom puff balls where you sort of puff and then
just losing bits.
Stuff goes out
off into space.
Yeah. So they're losing mass at sort of reasonable rates at this time in their lives as well.
So this is one of those.
Yeah.
Okay.
It looks pretty similar to this. So the actual mass of the star is not particularly different to the sun. It's kind of maybe around about a solar mass.
Right. But it's huge,
huge
in
so
size,
very,
in diameter.
Very rarefied, isn't it? Yeah.
Okay.
So kind of cool kind of star, isn't it?
That's a cool thing to come across.
Literally a cool star, but also...
cool and also in the kind of way.
Yeah. So let's summarise.
Yeah.
Pull all our bits of information
together.
Where
have we got to?
We've got this enormous M43 giant star that's in the process of mass loss, right? It's a very, very cool surface. It's not merging with another star because that would cause a much brighter event to happen and we would see emission lines in the spectrum.
We'd see that spectrum.
Yeah. Similarly, it's not going through any kind of nova explosions because we would also see that in the spectrum.
Strike that off the list.
We've got this clue that there's this dust that's happening around this star. And that's coming from the infrared.
And a fair amount of it.
Yeah, a third of the Earth of dust. And then we've got the energy that's been sort of released by this brightening event is really quite small. It's 1,000 times smaller than the energy that a star of the sun's size would release.
Sure. So when you put all of that together, where do you get to?
So you end up with, looks like this particular star swallowed a planet around about the size of Jupiter.
Right. Because that's like there's no other that they can see. There's no other models that say you just can't reproduce this unless you gobble up a planet.
Yeah, sometimes it does what it says on the tin. If you see what appears to be,
but walks like a duck, sounds like a duck.
Yeah,
probably
something the size of Jupiter got consumed by the star. I think it probably was a planet the size of Jupiter. Then,
what's the simplest explanation here?
Yeah.
So all of that dust is that the remnants of that planet? Like what is that?
It's a bit of the planet. It's a bit of the star. So
right. It's the remnants of that process of we just had a planet that just got ripped apart, encompassed by a star, and that just leaves you with a lot of dust.
Yeah. So we think that we've sort of got some evidence that this particular planet skimmed the surface of the atmosphere of this star, maybe for about 9 months before this brightening event.
That must have just looked wild.
Yeah.
It'd be great if you could actually see these things. I
mean, you can imagine just this ball, the drag of all the outer material of the star just going around it because it's going quite quick, right?
Yeah.
This is a planet that's close to its host star. Its orbit was probably less than a day before it was eaten up.
Wow.
So, yeah, it was whipping around, right? And so it was just in the atmosphere of the star. It was being dragged, lots of friction. Therefore, it was losing energy, moving closer and closer and closer to, the center of the star, effectively. And then it got to the point where it just sort of broke apart, released all this light that we detected in the transient survey, and a lot of dust just emission as well.
Yeah, I mean, the mental image of that is extraordinary. The fact that we can describe that scientifically is wild. It'd be so cool if we could actually see it. But yeah, one day, and that's what animators are for, right?
Indeed. And I reckon we have seen probably the closest that we will ever see, at least you and I, to this kind of event. It wasn't a planet being consumed by a star, but we do have actual real photographs and videos and everything else of a comet going into a planet.
Was that Jupiter? When was that?
Yeah, so that was Shoemaker-Levy.
That's right.
Yeah, comet Shoemaker-Levy impacted the surface of Jupiter, and we saw the disruption in the clouds of Jupiter. Well, we got infrared images of the impact event itself, and then the disruption that happened.
Well, because it broke apart, didn't it?
Yeah.
So weren't there like collisions over a period of, was it days? Yeah, I remember. When was that? Was
It
that
was around about 97,
I
something
can say
like
in
that.
the 90s, yeah. Again, well, we'll put a
Beautiful Hubble
link in the
images,
show notes because, that was wild.
I mean, that's the image that pops
Yeah.
to my mind when we're
Yeah,
talking
yeah.
about this kind of thing. Planet breaks apart and then just kind of gets subsumed into in this case, it's not, the cool, quote unquote, outer atmosphere of a planet. It's actually the really hot plasma of a star.
Yeah, but you're right. That's probably the closest that we can have to something where we've actually taken pictures of it, which is pretty cool. Okay, so that's really exciting. The fact that we've seen. Have we seen this before? Is
No,
this the first time we've seen this?
Very first time. But I think there's probably an element of which we're not really that surprised.
Okay.
In the sense of we totally expected to find these things, right?
Right. Okay.
So if you look at kind of the state of the nation of exoplanets and what we understand about exoplanets, it kind of seems obvious that we should detect these kinds of events.
Right.
And then what I mean by that is that there is actually a lovely paper which I'm going to go and dig down and read in really wonderful detail, and this is one of the topics I'm going to put up on the whiteboard of the state of the nation of exoplanet science.
The lovely thing about Emily doing all of this research, I mean, I just get to turn up and then do the editing afterwards of the podcast, but Emily does all the research, and the lovely thing is I get to turn up in her office and she goes, okay, I went down some rabbit holes for this one, and occasionally those rabbit holes turn into their own entire episode, so maybe this is one of those.
Oh, absolutely. It's a lovely paper. I haven't even read half of it. I've only just looked at some of the figures.
What's it on?
It's just about what do we know about exoplanets. It's a summary review article.
Right. Where are we at?
What do we know? Which is very helpful because it saves me reading thousands of papers, right? Which I wouldn't do anyway. So.
A good service to all astronomy kind.
Well, they're brilliant. I love review papers because they do represent a stupid amount of work by the people who write them, but they present information in a really nice, concise way.
So what does that tell us about the frequency of these sorts of things?
Well, we do know that we have lots of planets in our solar system, in our galaxy.
Yeah.
Planets going around other stars in our galaxy that had very short periods.
Right.
Right.
And a lot of these were the ones that we found pretty early on as
Indeed,
well.
some of the first, yeah.
Because let me see if I get this right, okay? Because they're generally big, and bigger means easier to spot. And because they're so close, they're going around really quickly, which means you get a lot of transit events, which means you can be pretty sure that it's an exoplanet much faster.
Yeah.
Because it's crossing in front of the star much more often. So
well,
easier
indeed,
to see.
it's not just transit. It's actually, I think the first ones even came out of just looking at the wobbles of stars,
Right.
the Doppler shifts.
Yeah, but the point is you don't
Same
have to
concept.
wait forever to see it happen again.
No, we don't want to wait 10 years to see a whole, to see a transit
It's
again,
happening on
or
the
to
scale
see
of
a
like
wobbler.
hours. Yeah.
Yeah, so we know there's lots of planets with these short periods, and as you say, we know there's quite a few of them that are Jupiter-sized. They may not be the most common types of planets in the galaxy, but we've spotted enough of them that
Sure.
we know that they're out there.
So eventually we ought to see one of them get gobbled up, is the point.
Well, that's clue number one.
Sure.
So clue number two is that we don't tend to see planets around these giant stars.
Okay.
Then once a star sort of starts evolving, starts to turn into some of these giants, supergiants, we just don't see planets anymore.
I see where you're going with this. And so because we don't see them, like why don't we see planets? Well, maybe they used to be there, but maybe they're not there anymore.
Yeah.
Oh, why? What happened to them? Well, maybe this is what happened to them.
Exactly.
Maybe they got gobbled up.
And indeed, when you go and look at the systems that we do have with these very short periods, very close to their host stars, they're not old systems. So they're not systems that have been hanging around there for billions and billions and billions of years.
Okay.
They're fairly young. So you've only got young ones that we do see. You go and look at the older evolved stars, you don't see them anymore.
There's no planets there anymore.
No.
What happened to the planets?
Yeah.
Think we might have just spotted one on the way out.
Exactly.
Yeah.
In fact, estimates say that maybe these kind of consumption events, if you want to
Nice.
call them that.
Is that what they're called? If not, they should be.
Oh, I'm pretty sure star consumes planet is a valid term in astrophysics now. But we expect one to happen maybe every 1 to maybe even 10 a year to happen in our galaxy.
In our galaxy.
Yeah.
Right.
Somewhere between 1 and 10 would happen every year in our galaxy, as we estimate.
So watch this space. We probably going to, I mean, this is the first one, but that's the floodgates open now.
Yeah, well, we know what we're looking for.
We'll be tripping over them all the time.
Well,
Another star
maybe.
eating a planet.
That's quite cool, though, isn't it?
It is very
You can
cool.
see.
It is cool. I like the way it's both completely expected and ordinary, and yet just so cool that we actually spotted one in the process of it happening. That's cool.
So the logical next sort of step, if you like.
This is where it gets uncomfortable,
The next
right?
leap in the imagination is,
Yeah.
okay, well, this was a fairly ordinary, probably solar-ish mass star that's now evolved into this planet-consuming monstrosity.
I can think of another solar mass star not terribly far away. Emily, is what you're alluding to here that this is ultimately our fate? Do we have this to look forward to?
Yeah, maybe.
Maybe? I mean, we're not an enormous Jupiter-sized planet orbiting around it with a period of a day. We're a bit further out and a bit smaller.
Yeah, but our sun is gonna blow up into one of these giants at some point. Yeah. So the sun will go through this giant phase.
Right.
It is gonna expand. It will definitely encompass the orbits of Mercury and Venus.
Okay, that's getting uncomfortably close even at that point.
Yeah, definitely all the other things. This is the other rabbit hole that I've pulled back away from to leave for another episode. The details of how the Earth is going to turn horrible over the next 5 billion years.
You read about that all day. That's fantastic.
Yeah. But the Earth's temperature is going to rise because of the increase in temperature of the sun. We will lose our oceans.
We think we've got problems now.
Yeah, well, this is we'll runaway greenhouse effect and the atmosphere.
You've got to have an atmosphere to have a greenhouse effect.
Well,
we're not going to have one at this point, surely.
Well, it'll be CO2, just CO2.
Yeah. Good.
That's all you need, and water vapor to have a greenhouse effect. It's just Venus, right? That's the.
I'm just thinking by the time that the sun is that big, won't we kind of pretty much lost our atmosphere anyway, from the sheer...
Well, this is before the sun even gets this big.
Yeah,
I mean, this is, earlier days. This is in the next kind of 2 to 3 billion years. Then all this is happening.
Yeah, I mean, that was going to be my next question is, do we have to worry about this anytime soon? I'm guessing no. We're talking timescales of like billions of years.
At least the best estimates say that in 2.8 billion years, the Earth will be uninhabitable.
Okay, good. Well, we've got a bit of time.
The surface temperature will be maybe somewhere around about 150 degrees.
Yeah, it's getting warm.
Yeah.
Warm.
So
how big will the sun be at that point? Like, has it really started to expand at that point?
Not too much. So that's only it's 4.5. That's 6. That's just over 7, right? Billion years of the sun's age.
Okay.
It'll have started because it will be brighter, and it's causing some
started its inflation.
But the main kind of engulfment period is somewhere between 7.5 to 8 billion years of time after. So the sun's currently at 4.5 to 5. So we're talking about up to when it's 7.5 to 8 billion years old.
So what I hear you saying is, don't worry about it because the planet will be utterly uninhabitable way before we get actually swallowed up by the star.
Well, yeah, but I mean, I think we've got to worry about the next 100 years, let alone the next few billion. But
put things in perspective.
It's still wonderful to play this out in our minds, right?
Yes, yeah.
So the wonderful thing, wonderful. Let's say the thing I find most intriguing about this whole thing is it's actually not obvious whether or not the Earth will be consumed.
Right.
We seem to be right on this kind of tipping point of will the Earth be eaten by the sun or not? Because whilst all this temperature rising and etc. is happening, it's estimated that the Earth may move, will move in its orbit. So we're currently at 1 astronomical unit from the sun.
By definition.
Yeah, because that's the distance that we have from the sun.
Yeah.
It's estimated that the Earth will move as the sun loses mass throughout this end point of its life. The Earth will move outwards to up to maybe 1.5 times the current distance. So that's kind of quite far away.
So the sun is losing mass, but it's starting to expand. It's getting bigger, but we're retreating.
Yeah.
We're moving away.
So the first question is, are we moving away fast enough?
Yeah.
Well, or far enough.
Game chase here.
Best estimates say that maybe the sun will come up to about 1.2 times the current
Might
orbit.
just skate around the edge.
But
thumbing our nose at it.
that would all be fine if you were only talking about loss of angular momentum.
Right.
So that process of the Earth moving outwards.
Right.
But of course, there's this other process that we alluded to before.
The drag part, where we'll be losing energy and spiralling in.
Especially because we've got all this extra mass from the sun that's
being
puffing
flung
out our way. Yeah. So that will pull us back inwards.
So any idea which one of those is going to win?
Well, no. It seems to be kind of all in the balance here.
Aren't we special?
Yeah, something like that. So, there's a 50-50 seemingly chance that the Earth will be eaten by the sun, or maybe it won't.
I mean, that's really interesting in a sort of very moot point kind of way. Is that a victory if we manage to avoid being eaten? I don't know. It's curious, though.
Well, yes. I mean, if you want to really put a fine kind of point on it, it will happen eventually.
Okay.
Because if you just run time forever.
Just keep that simulation going. Yeah.
Right. What happens is eventually the sun goes through all the rest of its evolutionary phases, turns into a white dwarf. That white dwarf cools down. We just have a blob of stuff, which used to be the sun.
Yep.
Basically.
And let's assume at that point the Earth is still there and it's still orbiting around said white dwarf.
Yep. This black dwarf at that
black
point.
Dwarf,
black
blob.
dwarf. Yeah, it loses its whiteness. It becomes black.
Right. Okay.
Because it's radiated all of its temperature.
Fun thing to look forward to.
That blob of Earth that's left over will eventually crash into
right. It'll just eventually just slowly but surely spiral down and go bump, and that's it.
Yeah.
It's a really depressing future to look forward to. I kind of like the whole let's get eaten by the big giant star bit. I think that's a better way to go.
Not the cold dark.
No, that just feels a bit too just it's giving up at that point. Just right, fine.
That's
done
usually
here.
how the universe works, is to play to our emotions, right?
That's right. On that existentially curious place to wind up the episode. I'm not quite sure how I feel about all of that, Emily.
No, but I want to do a whole episode on how the Earth is just going to be awful in the future.
Okay, yeah. Maybe that can be the first thing to go up on the whiteboard is awful ways for the Earth to go out at the end of days. But today, I'm not really sure how I feel at the end of this one. Listeners, if you want to get in touch and tell us how you feel at the end of this episode, do you feel sort of elated at the thought of being gobbled up by an enormous star? Do you feel slightly depressed at the thought of slowly spiraling down towards a black dwarf? Or does all of it seem a bit moot, given that none of us will be here?
Maybe we should just turn the lights off and just spare the environment.
Last one out, close the door behind you. So listen, if you want to get in touch with any of these thoughts, then there are loads of ways that you can do that. Emily, give us one.
You can go to syzygy.fm.
You can. What's there?
syzygy.fm. There is a wonderful little contact us page.
There is. It's really nice to check the email every once in a while and see, there's an email. Someone's got in touch with us through the website.
I wish I had there's an email response to opening my inbox.
I mean, how often do you actually get that's a nice email to get. So do get in touch, even if it's just to say, hey, we're out here and we're listening. It'd be like contacted by aliens from outer space. It's just nice to know that they're there, you know? Other ways that you can be in contact with us, we do the Instagrams at SyzygyPod, all one word, SYZYGYPOD. We are on the Facebooks too, in that way that you just do on Facebook, which is you just search for us, Syzygy Podcast. We're out there. If you want to support the show, there's a bunch of ways that you can do that. One of them is to just tell everyone you know. Get in touch with those friends, family members, people that you think would get a kick out of things like, how is the Earth going to come to an end? Tell them about the show. Point them in the direction of the podcast, because the more people who know about us, the more we're doing our job. In particular, you can give us a rating or a review, and that helps us to rise up through the podcast universe noise, and more people will be able to find us. The last way you can support us is, of course, you can become a financial member of the show. You can go to patreon.com/syzygypod and throw a couple of bucks, a couple of pounds, a couple of your own particular currency our way, and it helps to keep the electrons flowing through the website and helps us to do what we do. Otherwise, I mean, we're doing pretty well here, Emily. We've been managing pretty much roughly weekly for a little while now, so let's keep that going.
What's next week? Is it we have Black Hole Week? Is it?
I don't know.
Neutron Star Week? Or?
It's the coronation here in the UK, so maybe there's something regal astronomy.
There's the Crown Nebula, I think.
Oh, let's have a look
Carina,
at that.
yeah.
Look, we can't guarantee something royal themed, but we'll have a look at it. Probably the only thing that is going to be royal themed about the coming week for me. I don't know about you, Emily. Why don't we call it quits there? Listen, we'll be back again in roughly a week. Until then, Emily, catch you later.
See you later.
Bye, everybody.